Good afternoon, colleagues. We are now having a session for TC-27 seminar, Interdisciplinarity in Strategic Foresight for Infrastructure. I'll be your moderator for today. Our chair, Doc Benny, is online as well in the Philippines. It doesn't play. Okay. Oops. Okay. These TC-27, as approved on March 26, 2021 during the fourth ECM has the following objectives. Actually, it's promoting about future thinking, future literacy, and strategic foresight competencies among us civil engineers and civil engineering societies or institutes in order to integrate knowledge on strategic foresight across various disciplines and advocate basically sustainable development through long-term strategic planning for infrastructure from the design, construction, and maintenance. And hopefully we can publish a handbook or source book for civil engineering on this matter. This is how our program will run. I will make a brief introduction of who the speakers will be. I'll be the moderator. Currently, I'm the first Deputy Secretary General of ACECC, and is a member of the Philippines as well, of the Philippine Institute of Civil Engineers, the Philippine Technological Council, as well as the Philippine Federation of Professional Associations, being the Vice President representing the engineering cluster. Next speaker will be Hyung-Koo YOON from the Korean Society of Civil Engineers, who is an associate professor in the Department of Construction and Disaster Prevention in the Daejeon University, a specialist in geotechnical engineering, measurement sites, characterizations, and civil engineering education. He's a researcher and a practitioner in situ and laboratory tests for understanding soil behaviors, an application for machine learning algorithm to geotechnical engineering, risk management, and hazard assessment. Next speaker will be April Lander from ASCE, a member of the TC-27, a chair of TC-26 and co-chair of TC-24, and the ASCE representative to ACECC. She is the ASCE Director, Region 10 from 2022 to 2025, and a board member for Civil Engineering Certification, Environmental Sustainability Profession, and an independent contractor living in New Zealand. Her specializations are in water environment, emergency management, health and infrastructure, strategy, planning, education, JEDI, sustainability, and elections monitoring. Next will be Shermon CRUZ, who is the chair of Association of Professional Futurists. This is more appropriate for him because we're talking of the future. The chair of the Millennium Project Philippines Node, Chief Futurist, Center for Engaged Foresight, adjunct faculty of the Asian Institute of Management, co-founder of Global Future Society, Dubai Future Foundation, UNESCO chair candidate, anticipatory governance and regenerative cities, and many other more, as you can read. Then our chair, who's also a speaker, is Dr. Benito PACHECO from the Philippines, representing the PICE National Special Committee on Interdisciplinary Strategic Foresight from Infrastructure. He's a professor at the Institute of Civil Engineering, University of the Philippines, an academician member, National Academy of Science and Technology, also in the Philippines, and a specialist in structural engineering, environmental engineering, energy engineering, civil engineering education, and a researcher and practitioner in disaster risk management and Future thinking and strategic foresight. All of our presentations have been pre-recorded except for the one who's here on site with me, April. So we'll now go on with the presentations that have been pre-recorded before. First topic will be Interdisciplinarity of Landscape in Geotechnical Engineering by Hyung-Koo YOON from KSCE. We're having some technical problems.
Mr. Chair, perhaps this is the PowerPoint version, but there is a video version.
Please play the video. So it's the video. We marked earlier the PowerPoint. So it's the same file with the name of the speaker, but unmarked. What we marked earlier are the PowerPoint, which is 1, 2, 3, 4. Please play the one. Same file name, but MP4. Right, Doc Benny? MP4, right? That's right. It's MP4.
Right, the MP4 version.
MP4 file.
Thank you.
Yeah, it's Professor Yoon. Yeah, yes. First speaker is Professor Yoon. That's just PowerPoint, but he has a pre-recorded video present. Yeah. So they're looking. It's the same Google Drive, same same. Oh, this is Doc Benny. Uh, uh, online. Uh, so it's Professor Yoon MP4 file. Too big. You cannot download. Uh, who are we ready with April, Miss April? Okay, because you're on site, so it will be easier. It will be easier for you to do the presentation while they're downloading everything. Doc Benny, can you play your presentation from your end, or so you can start as well?
The bandwidth on my end is not so great.
Okay. Understood. Understood. I think April is ready now to do the first presentation.
Thank you. So I'm April Lander, as mentioned before, and I'm the ASCE representative at ACECC and also the ASCE Region 10 director. I'm happy to be here. I first want to thank our chair and also our distinguished panel and also our ASECC chair and KSCE for hosting this event today. Thank you so much. So today I'm going to talk about a free interactive tool developed by ASCE and its partners. And it's something that engineers can use to collaborate with others and it's to reimagine the world and shape the future. It's a very, very interesting tool. I think you'll find it interesting. So it's a desktop app. It's called Future World Vision, and it allows you to actually step into virtual worlds. So it's very exciting. Okay, hopefully that's a little bit better. So I'll just repeat what I said, just in case people missed it. So it's a desktop app. It's called Future World Vision. And you can see on the side here that it's available at futureworldvision.org. And I'm specifically going to talk about one component of it, which is Megacity 2070. And the reason I'm going to do that is because there's projections that 85% of people will be living in an urban environment around 2070. And of course, in Asia, that means quite a few cities are going to be megacities. So I think it's very important for us to think about what the future is going to be, how we as civil engineers in the engineering community, not just engineers though, all types of planners, everyone from different interdisciplinary disciplines can do this and have an impact on our infrastructure and how it's being developed. So what I'm going to do is just show you a few videos. One's kind of an introduction. Another is really looking at the sustainability, resiliency, and equity of future infrastructure. And the last is just a little bit of an orientation that will hopefully give you an idea of how it works and how you can go in and use it. It's very powerful. There's many tutorials about the different types you can look at, for example, water issues or alternative energy, or many different aspects of future cities. So with that, I will see if hopefully my videos will work. Doesn't seem to be doing the sound. Let me try another way. Getting help. I need to get to my, I need to get out. Make it smaller so I can see. I can get. First one. No, it's still the first one. Sure. Still not doing the same.
Our cities are incredible mosaics. Mega City Intro. Our cities are incredible mosaics, reflecting both our collective history as well as our vision of the future. Even though cities require vast resources, their urban density makes them the most efficient places on Earth. Yet urban centers that are unable to evolve to meet the challenges of the 21st century will be left behind as people look elsewhere to build their lives and communities. From 2020 to 2070, climate change and environmental conditions become more extreme, intensifying threats such as flood and fire. Population growth, demographic change, and urban densification add to these challenges. Over time, ever more people relocate to cities, attracted by progress, driven by technological innovation and efficiency, and drawn by the desire for education, culture, and entertainment. The urban migration is further fueled by climate refugees seeking the security of resilient cities. Megacity is one such city, a city of 50 million people in the year 2070. Megacity is a complex ecosystem of diverse and interdependent systems, structures, economies, cultures, and challenges. By 2070, Megacities' resources are decentralized, decarbonized, and modularized to accommodate ongoing innovations in materials, computing power, and transportation, as well as health and education. The success or failure of public policies adopted decades ago is evident in the quality of life provided to all residents. Digital models provide real-time feedback at all scales of infrastructure, and the vastness of data tests the limits of processing, security, and understanding. Energy and water become nested microgrids. Autonomous and aerial vehicles become intertwined with telecommunications networks. Megacity is a fictional place, but it's not fiction. Every street corner, every energy source, the qualities of the water, air, and soil, all are informed by the realities of cities around the globe, from New York to Tokyo, Los Angeles to Lagos. The interactions of every infrastructure system are based on real data and deep research gathered from experts across industry, academia, and government. Over the next 50 years, change and innovation will accelerate, and the unexpected will occur. Yet we will be prepared because we will walk these future streets today. Engineers of the future will understand the communities they serve as well as they do the mechanisms of infrastructure that enable humanity to thrive.
Okay, I'll see if I can get the next one to play, which is going to be related to sustainability.
Sustainability, resiliency, and equity. To sustain a population of 50 million people, Megacity must build resilience into every aspect of its resource management in order to optimize those resources for all the city's inhabitants. Even with the most valiant efforts to curb the city's impact on its environment, the effects of climate change must be planned for as part of normal life. Updates to utilities infrastructure have improved efficiency by integrating renewable energy generation and nesting microgrids within the larger city framework. This also makes the city more responsive to disasters or macro system failures. These strategic redundancies allow for redistribution of energy and clean water to neighborhoods that might otherwise suffer disproportionately when unforeseen events occur. Measures are taken not only to preserve natural resources, but also to regenerate them, scrubbing the air, healing the soil, and empowering overlooked populations all require innovation in methodologies and shifts in thinking. The deployment of adaptable infrastructure and building technologies are crucial for the city to meet its goals for a more sustainable, resilient, and equitable future. Building information models, or BIM, have simplified the codes and standards and have empowered residents to guide the evolution of their communities. Reconfigurability has further democratized the customization of spaces. Traditionally less affluent areas suffered from shade inequity as a lack of tree canopy left people exposed to heat and UV rays. Efforts were made to expand green space, and innovative approaches like these shade structures also photosynthesize, helping reduce temperatures and clean the air. In megacity, there are always more voices to consider. By digitizing the public square, like-minded individuals can identify each other and build coalitions to make change or advocate for services, creating a sense of equity and belonging. Public safety and restorative justice centers are true neighborhood hubs that handle mediations, job training, and mental health services, in addition to ensuring the safety of the community. Residents and tourists are encouraged to do their part to safeguard an area once taken for granted. A permit system allows one to earn recreation time at the river by participating in its maintenance and rehabilitation. Away from the relatively calm and breezy riverfront, the dense vertical downtown area has its own unique challenges. A five-fold increase in population over 50 years has not only affected the air pollution, but the amplitude of noise as well. Fortunately, large-scale reductions in noise at the source, like the electrification of ground and air transit, have alleviated some of it. But other noise control solutions are also found on the receiving end to abstract, manipulate, and further mitigate the sounds of the city. The high-rises of previous decades were known for their relative inefficiency. Thanks to new designs and materials, they're now more efficient than ever. The ability of new materials to retain and release moisture create buildings that breathe, reducing the cooling load by regulating fluids at the micro scale. As civil engineers look to the future, infrastructure alone won't be the sole measure of their accomplishments. They'll work together with other engineers, urban planners, and the citizens themselves to create the best quality of life possible. Resiliency must be considered from the planning stages to ensure that new projects can stand up to an increasingly unpredictable environment while equitably meeting the needs of the public.
Okay, and I have one more that's going to just show you a little bit more about how you can actually go into this platform and use it yourself. Because you can go in and you can create presentations on different topics. For example, just pull out specific information. You can input information and ask people to comment on it, for example, and get feedback on your own ideas as well.
After logging in and moving past the Tours and Tutorials screen, you'll be in the City View, where you will see a wide map of the city and the surrounding region. A comprehensive story of Megacity appears on the left. To see the map evolve over time, navigate to the year selector on the right and click through the other eras. An important feature of this view is the ability to see the city through several macro lenses. Clicking these allows you to isolate specific regional realities that shape the challenges and guide the innovations in Megacity. Refer to the legends to understand these lens layers, study the data that informs them, and read a brief overview of each. When you're ready to move on, you'll see that 6 distinct districts are selectable. Click these to read about how they differ. 2 of the 6 districts are more fully explorable. When you're ready to go deeper, click on either Historic Core or Adaptive Corridor, and those will lead you to those districts. Once the district view is loaded, you'll have several options to explore. First, the lens buttons have now been replaced by systems buttons, and this is the place to understand the systems of the city. Clicking through each, you'll see a new legend appear. An overview accompanies actual data that is driven by the population density, demographics, and energy and resource requirements of this particular district. Also in the district view are key landmarks that are crucial to understanding the wider functioning of the district and city as a whole. Rolling over the callout flags extruding from the landscape will display the name of that particular landmark. Click to explore them in more detail. Let's look at the energy substation. You can move in closer and read the summary of the landmark's function. Then you can click through the steps that illustrate the process in more detail, while seeing the landmark animate to further clarify. When you're ready to leave this landmark, X out and you'll return to the district. The next thing to see here is what is called a core sample, indicated with the explorable dark callout flag. Think of this as a detailed cross-section or a vertical slice of a few key city blocks. Upon selecting it, you'll notice that it's segmented into 4 distinct vertical layers. Selecting each, you can read the summary on the left, and then click specific callout flags within those layers to take a closer look. When you're ready to move on, click Enter Street in the lower left portion of the text window. There will be a brief load as all of the elements of the street corner populate. Once they do, you'll find yourself seeing the city at a human scale, the streets bustling with activity. Using the various navigation methods, and for more on this, watch the Navigating Megacity tutorial video. You can wander or fly around the street corner. You can click any callout flag that interests you and zip to that spot. Here you'll see 3 tabs. On the left, you can read the technical info to understand the engineering logic or explanation for this particular callout. Then read the narrative description, which explains how this item might impact residents in their day-to-day lives. The middle tab, Discussion, allows you to add your thoughts to the conversation, which in turn might spark colleagues to add theirs. Previous comments appear below, and you can reply to those as well. Note that you'll have a choice to post your comments to all users, which is the default, or if you are a member of a private group, you can select that group from the drop-down menu here to keep your comment private. The rightmost tab is the Research tab. Open this to find the research that informed or inspired the callout. It may be in the form of a video clip from an expert interview or citations for research articles. Bookmark the callouts you want to remember so they will appear in your library, making them easy to find later. When you've finished with the callout, simply click X to close it and continue on your way. Finally, there is a filter button you can use if you are only interested in seeing callout flags within a certain theme. You can find this button in the lower right corner. When you click it, a filter screen will appear with a few dozen keywords. Clicking the breadcrumbs or arrow-shaped banners at the top left of the application will help you jump back to any level you'd like to go, and you can continue your exploration from there.
So thank you for that. I hope that gives you some ideas of how this desktop app, like I said, is free for anyone, available at futureworldvision.org, can be used. And like I said, you can tailor it to your own specific interests and go from there. So thank you very much.
I guess that last comment of April answers Professor CRUZ comment that he wanted the link. So please repeat it. That's
Yes, it's futureworldvision.org.
so, okay. That's it, Engineer CRUZ. That's the link for that presentation by April.
I'll put it into the chat.
Okay. Okay. Thanks. Any other comment, probably from the on-site audience, or do we move on to the next presentation? I hope the video has already been downloaded. So it will be now for Professor YOON on interdisciplinarity of landscape in geotechnical engineering.
And the subtitle is Application Example in Geotechnical Engineering. Good afternoon, ladies and gentlemen. My name is Hyung-Koo from Daejeon University. I was in the KSCE. Today, I will present the interdisciplinary of landslide in geotechnical engineering. And the subtitle is Application Example in Geotechnical Engineering. And third, the subtitle is Estimation of Safety Factor Distribution through Machine Learning Algorithms. Before presentation, I had very shows my applies. I'm very sorry for presenting through the recorded cam instead of live presentation. Okay, from now on, I will start my presentation. The slide contents of my presentation. First, I will show the background theory. Second, methodology and results. And finally, I will show the conclusion. In this presentation, I had my objective of my presentation shows the how can the new technique is applied in geotechnical engineering. So I will show the target is the landslide. The landslide risk assessment, which called as LRA, there are two kinds of methods to estimate the LRA. First is probabilistic method, and second is deterministic method. In probabilistic method, the historical literature data, whether the determined value exists, the reference value. The probabilistic method can estimate the LRA through the probability of occurrence. And the methods necessary the large amount of accumulated data, including rainfall and intensity. The second method is deterministic method. The geotechnical and hydraulic property were applied to find the LRA. And the method provides the quantitative safety factor in a landslide. This method is also has limitation on the time and money consumed in obtaining various input parameter and each grid. To overcome the deterministic methods, the John suggests the empirical basis model called as the HRA method. The method is combination between the analytical hierarchical process, AHP, and expert advising group. The HRA method has three kinds of criteria: soil structure and particle distribution, stress and strain of soil, and soil and water. And the three kinds of criteria has eight kinds of alternative fine contents, void ratio, fluid thickness, elastic modulus, shear strength, hydraulic conductivity, saturation, and water contents. The alternative parameter shows in the geotechnical parameter to estimate the landslide risk area. First time, the research of John suggests the equation of the HRA to calculate the high risk area through the 8 kinds of alternative parameter. However, there has the different unit and different range of values as the reliability is reduced. And third, in this method, we suggest a new concept to increase the reliability of the HRA through the machine learning technique. And in this case, we use the theme map based on the Moore-Coulomb failure law in infinite slope to obtain the real reliable safety factor. In this study, we use 3 kinds of methods to find the relationship between input and output parameter. First is linear regression, second neural network, and third is random forest. In particular, in random forest, the multiple decision tree based on the ensemble model, we used OOB data through bootstrapping aggregation. As I mentioned before, we applied the linear regression and neural network. In the linear regressions, two kinds of methods in LR and NN has the common input parameter and final output parameter. The difference in LR and NN is the activation function and hidden layers. In the case of NN, we use the three kinds of optimization algorithms: gradient descent, LM, and BR to find the reliable weight and bias. And the hidden layer also used to calculate the high reliable weight and bias through MSE values. We use the and train validation and test ratios to 70, 15, and 50s. And through the LR and NN, we would like to get the relation between input and output parameter. From before the applying the LR and NN, we should have to get the obtain the geotechnical parameter in objective area. The slide shows the methodology. We can get the geotechnical parameter in Gwaeha Mountain placed in South Korea. The area has already experience of the landslide, so there is the check dam was also installed. We applied the field and laboratory test, elastic wave survey, electrical resistivity survey, dynamic compenetrometer, time domain reflectometer to find the soil depth, elastic modulus, porosity, hydraulic conductivity, shear strength, and volumetric water contents. And we also additional experiment for find steep test through the obtained specimen. So we get the data set basis on the experimental data. We divided the 1,800 grid cell of 1 meter each, and we get the 16 positions in the geotechnical parameters. In this case, we use the oversampling is necessary. So we use a geostatistical technique through the Weyl game and kriging. In this case, the seal, nugget, and range is very important to find the reliable geotechnical result. The graph shows from the fine contents to friction angle. So the each parameter shows the different range, seal, and nugget values. Through this geotechnical data, we can get the distribution of geotechnical parameter in the objective area in all kinds of 1,800 grid cell. This figure shows the 3D counter map basis on the geotechnical parameter. The graph is drawn before with using the geostatistical result from the fine contents and friction angle. The counter map also shows we get the high reliable geotechnical parameter in each grid, in all kinds of grid to perform the LR and NN. So the slide shows the results of the linear regression. So we use 3 kinds of the methods: gradient descent algorithm, LM, and BR. The 3 kinds of methods shows the high reliable. The R-square value is 0.9, 0.9, also 0.9. This slide shows the result of neural network. We plot the between predicted safety factor and actual safety factor. According to the node number of 1, 10, 100, the slide shows the all kinds of data shows around the 0.9 of R-square, and in particular, the high resolution shows when the number of nodes is 100, and according to the optimization methods, the gradient descent, LM, and PR also shows the similar result with a high resolution. Third point is we use the random forest, which parameter is important to calculate the safety factor in HRA method. In this case, distance tree is very important. We use the out of back mean square error to find the number of distant trees. As you can see, this result we can select the number of distant tree on the around 20 because the square error looks like a similar trend. So we use the distant tree of 20 to perform the random forest. The result shows the random forest result. Among the 8 kinds of geotechnical parameter, the shear strength shows high influencing factor in the HRA. The point is 0.38. And the saturation shows the low affecting factor in HRA. That means a relatively comparison, so there is no quantitative values. Anyway, we can get the high reliable factor from the shear strength to saturation, and we changes it. The result shows the possibility we can when it is difficult to get the 8 kinds of geotechnical parameter in the field, we can select the high influencing factor from the shear strength. So we applied from the shear strength and soil thickness, and finally saturation to increase one by one the influencing factors in geotechnical parameter. As you can see, these figures, when we applied the only parameter, the shear strength, the RMSE error is around 0.05 to 0.1. And the RMSE error decrease when we increasing the input parameter, number of input parameters. And when we applied the number of input parameter 4 kinds of geotechnical parameter, shear strength to fine contents, from the times the RMSE error shows the constant value. And thus we can predict. It is difficult to find all kinds of geotechnical parameter. We recommend the 4 kinds of geotechnical parameter at least can provide a reliable result of safety factor. And the comparison of landslide susceptibility based on the steam map, linear regression, and Euroletter. The bottom of the figure shows when we applied from the 1 variable to 8 kinds of variables. So as I mentioned before, 4 kinds of variables good to find the geotechnical parameter. So when we apply the only one variable, the distribution of safety factor is slightly different. The true variable steam map, the safety factor calculated based on the steam map. However, when we compare this figure and 4 kinds of variable, the distribution of safety factor looks like similar. Okay, finally, I will show my conclusion. In this study, I will show how can the interdisciplinary to application in the geotechnical engineering through the machine learning technique to find the high risk areas. We use the NN, LR, NM, and random forest. And through this technique, we find the high reliable geotechnical parameter. And through the random forest technique, we can suggest the 3 or 4 main factors is enough to get the quantitative susceptibility of slope. Thank you very much for my presentation. Thank you.
Thank you for that, Professor Yoon. Professor Yoon is online, and if you have any queries, we can raise or any comments on his presentation. Otherwise, we go to the next video presentation of Engineer Shermon CRUZ of the APF. You can play now. Okay.
Make, think, imagine, from questioning to prototyping the future. Here is the outline of what I'll be sharing with you today. Strategic foresight, the transdisciplinary field, the Association of Professional Futurists Transdisciplinary Initiatives and Strategic Foresight, and some cases, from questioning to prototyping the future, the engaged foresight approach, and where do we go from here? Strategic foresight is generally considered a transdisciplinary field. It draws on various disciplines, including economics, sociology, psychology, political science, engineering, architecture, physics, neurosciences, cultural and technology studies, among others. It involves analyzing trends and drivers of change, spotting wicked and weak signals, understanding the complexity of society, environment, and systems that we operate in, and considering multiple possible, probable, and preferable futures using scenarios and leveraging on our capacity to imagine and prototype these stories or narratives of the future. As a transdisciplinary approach, strategic foresight practitioners can bring together diverse perspectives and knowledge to create more robust and inclusive futures. This can be particularly important when dealing with complex problems that require a multidimensional understanding of the issues at hand. Imagine a city that wants to plan for its future growth and development. The city leaders could use strategic foresight to create long-term vision for the city that considers various factors such as demographic changes, technological advances, environmental sustainability, and economic trends. To do this, city leaders might bring together experts from different fields, such as urban planners, economists, engineers, sociologists, environmental scientists, and technology experts. They would work together to analyze trends and drivers of change in their respective areas of expertise and identify potential scenarios for the city's future. Through a collaborative process that we call participatory futures approach, the team might identify a range of possible futures, such as a future in which the city becomes a hub for green technologies, or a future in which it struggles with population decline and economic stagnation. By considering these different scenarios, city leaders can make more informed decisions about the policies and investments needed to create a more desirable future for the city. And by using a transdisciplinary approach, they can ensure that their vision is grounded in a comprehensive understanding of the complex factors shaping city futures. Imagine a company that designs and manufactures automobiles. The company could use strategic foresight to anticipate and prepare for potential disruptions in the automotive industry, such as shifts in consumer preferences, change in regulations, or technological breakthroughs. To do this, the company might bring together a team of experts from various fields, such as mechanical engineering, material science, design, marketing, and strategic planning experts. Together, they would use foresight methods such as trend analysis, scenario planning, and expert consultation to explore different possible futures for the industry. And through a collaborative process, the team might identify a range of possible future scenarios, such as a future in which electric vehicles become the dominant mode of transportation, or a future in which self-driving cars revolutionize the industry that would have significant implication to the future of road infrastructure, and future of road safety. So by considering these different scenarios, the company can make strategic decisions about research and development, product design, and market positioning to stay ahead of the curve and remain competitive in a rapidly changing industry. Again, strategic foresight as a transdisciplinary approach, the company can draw on a range of expertise and perspectives to create a more comprehensive understanding of the complex factors shaping the industry's future. This can help the company identify opportunities and challenges that a more narrow disciplinary approach might overlook. Last case. Imagine a city that wants to plan for the impact of climate change on its infrastructure. The city could use strategic foresight to anticipate and prepare for potential hazards such as flooding, sea level rise, and extreme weather events. To do this, the city might bring together a team of experts from various fields such as civil engineering, urban planning, environmental science, and risk management. Together, they would use foresight methods such as climate modeling, scenario planning, and stakeholder engagement to explore different possible futures for the city. Through this collaborative process, the team might identify a range of possible future scenarios, such as a future in which the city experiences more frequent and severe flooding, or a future in which heat waves and droughts become more common. So by considering these different scenarios, the city can make a strategic decision about its infrastructure investments, such as building seawalls or relocating vulnerable population. The city can also prioritize investments in resilience, such as upgrading stormwater systems or promoting green infrastructure. By using a transdisciplinary approach through strategic foresight, the city can draw on a range of expertise and perspectives to create a more comprehensive understanding of the complex factors shaping the city's future, particularly its infrastructure. This foresight method can help the city identify risks and opportunities that might be overlooked by a narrow disciplinary approach and develop more effective, robust, and sustainable solutions for the challenges it faces. The Association of Professional Futurists is a global community of foresight practitioners dedicated to promoting professional excellence and demonstrating the value of strategic foresight and future studies for their clients or employers. Members of the Association of Professional Futurists work in global corporations of many kinds and services, small businesses, consultancies, education, nonprofits, and government. It was founded in 2002. The IPF now includes more than 600 members from 50 countries. APF sets the standard of excellence for professional foresight practice. Members include futurists and foresight practitioners from businesses, governments, nonprofits, consulting companies, educators, and students in future studies. And APF plays a unique role in the field of strategic foresight by defining the competencies of professional futurists, the knowledge base of future studies they use, and the standards by which they work can be evaluated. The mission is to advance the practice of professional foresight by fostering a dynamic, global, diverse, and collaborative community of professional futurists and those committed to futures thinking who expand the understanding, use, and impact of foresight in service to their stakeholders, their disciplines, the communities that they serve, and the world. So, futures thinking is a critical skill for individuals and organizations that want to be proactive and adaptive in the face of rapid change and uncertainty. By engaging in futures thinking, individuals and organizations can better prepare for future challenges and hunt for opportunities and develop the needed strategies for achieving their goals in a rapidly changing world. One specific approach is the Engage Foresight Framework or approach that can be applied in different domains and disciplines and industries. And this is the framework that I've been using in the last 15 years of my foresight practice. The Engage Foresight approach is a collaborative and participatory approach to foresight that emphasizes the active involvement of stakeholders and the co-creation of futures. This approach seeks to create more inclusive and democratic futures by engaging diverse perspectives and values in the foresight process. In the engaged foresight approach, stakeholders are involved in every stage of the foresight process, from identifying the key issues and uncertainties to exploring possible futures and developing strategies for action. The approach emphasizes the importance of dialogue, mutual learning, and shared ownership of the outcomes. Engaged foresight is often used in contexts where the issues at hand are complex and contested, and where there are multiple stakeholders with different interests and values. The approach can be used to explore a range of futures and help stakeholders develop a shared understanding of the challenges and opportunities they face. Engaged foresight often involves a range of methods and tools, such as scenario planning, backcasting, visioning, prototyping, causal layered analysis, and these methods and tools can be applied in a variety of contexts, from community development to corporate strategy to public policy, innovation, and strategic visioning. Ultimately, the engaged foresight approach seeks to empower stakeholders to shape the future in a way that aligns with their shared goals, values, and narratives. Strategic foresight units and the discipline itself, the field in general, are becoming increasingly common in larger organizations, particularly in sectors such as energy, space, entertainment, engineering, technology, finance, and governments. So, where do we go from here? I would like to pose 3 potential questions that you might want to use to ponder and reflect on the future of civil engineering education and practice, let's just say in 2050. So when you think about the future of civil engineering education and practice in 2050, do you think things will mostly stay the same, or will it be dramatically different? Are you mostly worried or optimistic about its futures? How much control or influence do you personally have, or the organization personally has, in determining its futures? Thank you very much.
Thank you very much, Professor CRUZ, for that enlightening about the futuristic approach. Are there any? Is there any reaction from our on-site and off-site participants? If none, let's go to the presentation, to the video presentation of Professor Benny PACHECO from the PICE, the chair of the TC-27. On this interdisciplinarity, is there room for it in the undergraduate engineering education's future?
Interdisciplinarity. Is there room for interdisciplinarity in undergraduate engineering education's futures? Today, let's observe the short agenda as shown on this slide. First, let's speak about our possible futures and how those are shaped by many agents of change. There are pools of the future caused by agents of change such as social, technological, environmental, economic, and political. There are pushes of the present, like the momentum to go interdisciplinary in addressing complex problems of the world. And there are weights of the past, like the tendency to go deeper and deeper into specializations in what look like academic silos. Second, what is interdisciplinary? A quick search by Google would get as many as 410 million results. Topmost would be an oversimplified definition such as interdisciplinary involves the combination of multiple academic disciplines into one activity. followed by many examples of interdisciplinary journals and academic departments in universities, and master's degree programs and research projects, and more of those, up to hundreds of millions of examples. Meanwhile, if we did a search of journal articles, say until year 2022, we could find nearly 100,000, tagged as interdisciplinary in the title, abstract, or keywords. There has been an accelerated increase in the cumulative total number of articles over the past 100 years. Looking at 5 journals with the top numbers of accumulated articles, there have been overall increases over the past 50 years. And we might ask, under what subject areas? These are all the subject areas in such databases. Admittedly, these subject areas are not fully exclusive of each other, but authors would consent to associate their articles with any of these subjects. So, let's observe in the 4 subject areas of arts and humanities, engineering, medicine, and social sciences. Here are the subject areas where interdisciplinary has been highlighted by many journal articles. While 26% were under medicine, only 4.3% were in engineering. By the way, there have been indications that multidisciplinary is treated different from interdisciplinary. Indeed, interdisciplinary is treated different from transdisciplinary. Multidisciplinary, interdisciplinary, and transdisciplinary are not one and the same. We could go by definitions, descriptions, or typologies from this handbook of year 2017, for example. In the middle of today's agenda is interdisciplinary or interdisciplinarity. It is described to involve interacting, integrating, focusing, blending, and linking, the intra-academic integration of different types of disciplinary knowledge. In contrast, multidisciplinary, on the left, is much less than that. It is merely coordinating among disciplines. In contrast, also, transdisciplinary, on the right, is much more than that. It is fully synthesizing all knowledge that is co-produced among academic and non-academic actors. In today's agenda, we presume that interdisciplinarity is what we need with undergraduate engineering education. Third, let us give the examples of 11 engineering professions in the Philippines, as they are regulated both at the level of higher education and upon entry into professional practice. Basic education in the Philippines has been recently reformed, prompting revisions of higher education by year 2018. The Commission on Higher Education, or CHED, regulates the Bachelor of Science programs in engineering as well as in other higher education. The Professional Regulation Commission, PRC, regulates the practice of 45 professions, including 11 in engineering. To our knowledge, these 11 engineering professions started to be regulated by government at different times, from more than 100 years ago. From more than 100 years ago, if we arrange the 11 chronologically, we note that civil engineering was among the first. And the revisions in professional regulation have been coming at different years too. Civil engineering, notably, has not been revised since 1956 or 1950. Meanwhile, as shown in blue on this slide, distinction has been legally formalized for registered electrical engineer and professional electrical engineer. Similarly for professional mechanical engineer and for professional electronics engineer. As for higher education, as one of the requirements for entry into the practice of profession, all Bachelor of Science in Engineering programs were prompted for revision in 2017 and new implementation starting in 2018 after the nationwide reform in the K-12 basic education. Note that the 11 engineering programs had mostly independent policies, standards, and guidelines as contained in separate CHED memorandum orders with different numbers as shown on this slide. So let's examine the program structures, where they are similar and where they are different. All Bachelor of Science and Engineering programs are nominally 4-year programs. They vary in terms of number of units over the 4 years, from 113 units in mining engineering to 129 units in sanitary engineering, or by about 14% difference. In the non-technical, they have common courses among engineering students and indeed among non-engineering students as well, such as physical education and national service training program. In the non-technical as well, the general education courses in the core or required curriculum have been updated too. General education courses or basic sciences or basic courses have been updated to include technopreneurship. Up to here, the non-technical courses constitute about 30% or almost 1/3 of the 4-year curriculum. About 70% or more than 2/3 of the 4-year curriculum are technical courses, including math, physics, chemistry, and biology. And most of the basic sciences or basic courses. And at the bottom of this list, big chunks of so-called common or core professional courses for each major, such as civil, mechanical, etc. There have been trends of separating the CE professional courses from the professional courses of other majors. The earlier in the curriculum, the better, supposedly, for meeting the expectations of the professional practice. In large colleges and departments, for example, there are separate subjects or separate classes of numerical solutions to engineering problems and numerical solutions to civil engineering problems. More differences in direction are observed in the so-called specialized or track type of professional courses. 2 of the 11 BS engineering programs do not require such. 5 other BS programs require 1 or 2 semesters to include 1 to 3 such specialized courses with a total of 3 to 6 units, at most representing about 5% of the curriculum. Among the remaining 4, BSCE requires the most specialized courses in a particular track, namely 15 units or about 12% of the curriculum. And uniquely, the BSCE program policy also mandates that the track of specialization is to be written in the diploma, as for example, BS Civil Engineering with specialization in structural engineering. These are examples of specialized fields as generally acknowledged by the CHED and/or the PICE. Meanwhile, concerns have been raised by some members of the PRC as to whether or not good to brand the bachelor's diploma not only as civil engineering but also with any of these specializations. A nagging question, for example, is structural engineering a separate profession now from civil engineering? Fourth, we arrive now at some examples, some illustrations of debate in the academe and industry as shown here. BSCE education should conclude with specialization in one track versus BSCE education should equally cover all 5 or 6 specialized fields within in an integrated manner. Or here, BSCE should be the degree requirement, among other requirements, for professional civil engineer versus Master of Engineering Civil Engineering should be the degree requirement, among other requirements, for professional civil engineer. And as of now, we in PICE are in the midst of recommendations such as shown here: multisectoral interdisciplinary setting of qualifications for professional engineering and the corresponding bachelor level preparation, review of relevance of professional master or master of engineering degrees in the practice of engineering professions, and review of relevance of Bachelor of Science, Master's, and Doctorate degrees in industry as well as in academe. Fifth and finally, we get to inquire, how about civil engineering education in other parts of the Asia Pacific? How are the prospects of interdisciplinarity in the BSCE education? So we look forward to exchanges of ideas and approaches in ACECC, ACECC as well. Thank you for your attention.
Thanks, Doc Benny, the chair of TC-27. That wraps up our, just on time, just wraps up our session for TC-27. Thank you very much for your kind attention.